Good morning. My name is Steve Minnie, and I'm the Senior Director of Applications of the AFM Business Unit at Bruker, and I'd like to welcome you to this installment of the Bruker AFM webinar series. This presentation is titled The AFM Probe, Fundamental Selections and Applications, presented by Sean Hand. Before I introduce Sean, I'd like to make a few quick logistical comments. First, we encourage your participation during the webinar, and if you have a question, please type it into the questions dialog box. We'll accumulate all of the questions that you have throughout the presentation, group them together, and answer them all at the end. If we have too many questions or we're not able to get to yours, we will certainly follow up to your question by email. Also, if you'd like to review the presentation or you'd like to pass it on to a colleague afterwards, it will be posted later today. As a follow-up to this email, you'll receive that link to where it's posted. You'll also be able to see the archive of all the previous webinars as well. Finally, when you exit the webinar, we're going to ask that you take a brief survey. We'd really appreciate it if you could take the time to complete this survey, as it helps us pick the topics that are most interesting to all of you and generally helps us make the webinar series better. So let's get started, and let me introduce our presenter, Sean Hand. Sean is a senior applications scientist with Bruker Nanosurface Business. He's been at Bruker for 13 years, focusing on applications for automated AFM for high-volume semiconductor manufacturing, and he has many publications as well as a book chapter in that field. Sean has a BS and an MS in physics from the University of Vermont and has used thousands of probes in the process of achieving these accomplishments. So let me now turn it over to Sean for his talk titled The AFM Probe, Fundamentals, Selections, and Applications.
Good morning. Thank you very much, Steve. I'd like to welcome you to this morning's webinar, the AFM Probe, Fundamentals, Selections, and Applications. My name is Sean Hand, and I will be presenting the material this morning, but I'd also like to mention that this webinar has been a huge collaboration between the entire Bruker AFM applications team. So, just a brief introduction here. The appropriate selection of an AFM probe can be one of the most important decisions that you make towards a successful AFM experiment. However, there are many, many probes from which to choose, and this selection may appear daunting. What we hope to do in this morning's webinar is to enable you, the AFM researcher, to select a probe like an AFM expert. So as a brief outline of what we'll be covering this morning, we will do a brief probes overview in which we will look at some of the key metrics for choosing a probe. Then we're going to go through and on an applications base, look at different types of decisions that you need to make when selecting a probe. The applications that we'll be covering will be very high resolution imaging, quantitative nanomechanical imaging, fast scanning in both fluid and in air. We'll look at some biological applications and some force spectroscopy as they relate to biological applications, some nanoelectrical, and here we will focus on KPFM, nano-optical, in which we're going to focus on TERS. We're going to then discuss some probe preparation methods and cleaning, and finally we will review the Bruker AFM website before concluding this morning's webinar. So, the basic operation of the AFM, the SPM. So shown here is the basic schematic diagram of the scanning probe microscope, or SPM. For all it enables, the basic operation of the SPM is incredibly simple. So simple that AFMs have been made out of Lego and can also be found in high school science fairs. However, don't let that fool you about the power and the sophistication of state-of-the-art AFMs. The underlying physics of many modes of operation is still not fully understood, and the technology and intellectual property contained within every system is staggering. The simplest way to describe the operation of an AFM is to think about how a blind person reads a page of Braille. They move their fingers across the top, from the top left corner of a page, and then raster scan their finger back and forth down the page, mentally keeping track of where the finger is on the page and visualizing the bumps in the Braille to create an image of the exact text in their mind. This is exactly how an AFM works. So on the schematic, these parts are represented by the sample, which would be like the page, the scanner, the finger, and the probe, the finger, the laser controller, and the image. That is an AFM. And in many ways, exactly how the stylus profiler works. and you could even say the same of an old-fashioned record player. So what differentiates an AFM from a stylus profiler, and why is it so spectacular? The answer comes down to resolution. There are many enabling technologies in the AFM that enable this resolution, but 3 are unique to the AFM. The apex of the AFM probe is on the scale of the size of atoms. The AFM is sensitive to the scale of atoms, and the AFM senses forces on the scales of atomic bonds. All of these characteristics are unique, because of the unique geometries and capabilities of the probe. And these are often critical factors in determining the optimal probe for an experiment. So I'd like to go through these in a bit more detail. First, let's discuss the probe apex. This is a critical factor for determining the AFM's resolution. The AFM probes come in a variety of shapes and sizes to meet many different application needs, from biological to semiconductors. The 2 most common workhorse probes are the standard tapping etched silicon probes that we've outlined here in green. Also shown here are examples of specialized probes for many different applications, from high aspect ratio measurements, thermal AFM, scanning tunneling or STM, and even probes designed for sidewall interrogation. Most of these probes are either sharpened pyramidal silicon or silicon nitride for cells, such as the MLCT, which will be released here in December of 2013, which we've outlined here in yellow. AFM sensitivity. An AFM must be very sensitive to small forces so as not to damage the probe or the sample as the probe is scanned over the sample surface. In the diagram here at left, A is the difference from the reflected laser spot as it travels over the split photodiode. From the optical lever equation shown here, the length of the cantilever is in the denominator. Thus, reducing this value for a given system will increase the delta A, and a shorter cantilever will have a larger response for a given system configuration, and a shorter cantilever, therefore, is a more sensitive cantilever. The optics and electronics of the detector are important as well. The leading terms are all photodiode and electronic noise terms, such as the efficiency, total power, attenuation, index of refraction, sensor constant, and transimpedance. Notice, though, that the size of the spot, i.e. the focus in A, also matters. Like the cantilever length LC, the spot size is in the denominator. A smaller spot will give increased sensitivity, and this is why in our fast scan systems we have variable size spot settings. But there is a trade-off. Reducing the cantilever length does have its drawbacks. As you reduce the cantilever length, the spring constant K of the cantilever increases as the cube of the cantilever length. A higher spring constant for the lever means a higher tip sample force, which is not always desirable, as this can lead to tip wear or sample damage. To mitigate this, we look at the equation used to calculate the spring constant of the cantilever, where L is the cantilever length, E is Young's modulus, W is the width of the cantilever, and T is the cantilever thickness. To bring the spring constant down, as the cantilever length goes down, the cantilever is thinned as the thickness goes as a cube in the numerator. To summarize, we want the length of the cantilever L to be short, less than 200 nanometers for a good signal to noise, and in order to keep the spring constant K low to be soft, the lever has to be thin. So now when we look at the dynamics of the cantilever, for many applications the resonant frequency is important as well, either through observing the dynamics of an oscillating lever such as in tapping mode, or ensuring that there's no cross-coupling scanner motion into the cantilever. In general, the higher the resonant frequency of the cantilever, the better. As the resonant frequency scales with length squared, the thickness must be scaled independently of each other to achieve the desired cantilever dynamics. There's lots of engineering that goes into all of our small cantilevers. As we push the speed and resolution of the AFM, new probe and cantilever shapes have become necessary. As you can see here with this unique paddle-like shaped probe, the high-resolution scan assist air. So lastly, as a point of order, AFMers will routinely use terms expecting them to be interpreted in the context of an application and not absolutely. Some common examples of this are when AFMers talk about probe coatings, spring constants, and resonant frequencies. Coatings on probes have several different purposes. In the context of an electrical mode, such as tuna, This may be a conductive coating on the probe to allow for a better signal. This would be a front-side coating. Other examples of coatings would be carbon or DLC on a probe to extend the probe lifetime. Most probes also use a backside coating to increase their laser reflectivity, the amount of signal that reaches the photodetector. These coatings are generally referred to, or they're generally preferred as they mitigate some of the common image artifacts, but it should also be noted here that in some cases the coatings can in fact induce drift or contribute to contamination. The spring constant as well is very application context specific. What is soft in one application may be hard in another. This is similarly true for high versus low resonant frequencies. So in general, when talking about probe qualities, we want to make sure that what we do so within the context of the application for which the probe is being used. So, with that said, let's move on to discussing some of the applications and of the probes chosen for those applications. We will start with the most common of AFM applications, very high resolution imaging. So here we have an image of mica image in tapping mode in water. We can tell that the image is truly the sample surface and not an example of lattice imaging, but the 2-point defects image highlighted here in the red circles in the left image. To acquire this image, a probe was chosen as a very sharp apex. Remember that the apex must be smaller than the features on the surface being imaged in order to resolve those features, the microscope maker's rule. And we want a moderately stiff cantilever in this case to help preserve the probe during lifetime, the probe during imaging. Though all AFM probes are sharp, not all AFM probes are sharp enough to achieve this level of atomic resolution. It may take several attempts with different probes to find a probe that is sharp enough to achieve the desired resolution. From an operational point of view, we want to minimize the peak tip sample forces, and we want to localize the tip sample interaction. To do this, we operate with a very low free air amplitude and set the amplitude set point as close as possible to the free air amplitude while still being able to track the sample surface. Probes recommended for this application would be the ScanAssist fluid with a low spring constant of 0.7 newtons per meter, or the Fast Scan B probe with a spring constant of 4 newtons per meter. Next, we're going to look at some high-resolution imaging in air. In this application, we're looking at a high-resolution image of PDA in air. The adhesive forces in air are generally too high to achieve this resolution with tapping mode. So, in this case, we're using Bruker's PeakForce tapping mode to achieve this high resolution in air. PeakForce tapping does not depend on the amplitude and is therefore capable of high-resolution imaging in air. Just as in the case of mica in water, the sharpness of the probe determines how high of a resolution we will be able to achieve, and finding such a sharp probe may take several attempts. As for the cantilever in this case, we want to use a probe that has a very low spring constant, less than 1 newton per meter, in conjunction with a low set point to preserve the tip. For this example here, the recommended probe for a high-resolution PeakForce tapping in air would be the ScanAssist fluid with a low spring constant of 0.7 newtons per meter, or the Fast Scan C with a low spring constant of 0.8 newtons per meter. PeakForce tapping can also be used for high-resolution imaging in liquid. In this case here, we are looking at 2 channels of data. The first is the topographical data, and the second is a map of the sample stiffness. DMT Modulus is a nanoscope data channel that allows researchers to interrogate surface mechanical properties, a full description of which is outside the scope of this presentation. But what is important here is to be able to measure the relative stiffness of the material, in this case calcite, with PeakForce tapping in fluid. Here again, to achieve the high resolution, we need a very sharp probe, and finding this probe may take several attempts. In this case, though, we have to consider the stiffness of the cantilever for a new reason. In order to achieve the good contrast in the stiffness map, a moderately stiff cantilever is required. In the context of this experiment, moderately stiff is on the order of about 5 newtons per meter. Probes that are recommended for this type of experiment are the ScanAssist fluid or the ScanAssist B probe. And for our last example, we're going to take a look at some high-resolution imaging of DNA. Here, PeakForce tapping is again used in fluid to image DNA that is loosely bound to the sample surface. What is amazing here is that we were able to see both the major and minor grooves of the double helix. To achieve this high resolution, a very sharp probe is required, and a short cantilever with a very low spring constant increases the sensitivity and at the same time protects the tip and loosely bound sample from sample damage. The probe best suited for this application is the Fast Scan DX with the short 18 micron cantilever and low spring constant of 0.25 newtons per meter. So, to review, some key points for selecting probes for very high resolution imaging. So the resolution of the given AFM, of the given image is determined by the apex of the probe. So a small tip is able to resolve features without influence from neighboring structures. We want to, for high resolution imaging in air, we want to use PeakForce tapping rather than tapping mode, or to move towards imaging in fluid. We want a short cantilever. As we mentioned earlier, the short cantilever provides greater sensitivity. And we want to select our spring constant to avoid tip and sample damage. And lastly, for considering the resonant frequency, we want to make sure that the resonant frequency of the probes is greater than the modulation frequency by about a factor of 10 for PeakForce tapping. And for tapping mode, we generally want a probe that has a resonant frequency on the order of 10 kilohertz. So, in the last section, we had a brief introduction to quantitative mechanical measurements, or more commonly known as Q&M, in looking at the stiffness of the calcite measure with the PeakForce tapping. Now we're going to explore the probes that are used for Q&M in more detail. Q&M is a broad term covering a number of different AFM techniques, including PeakForce Q&M, force volume imaging, nanoindentation, and force spectroscopy. The theory behind Q&M and the modes just mentioned are again beyond the scope of this presentation and are well documented elsewhere. I encourage you to download and view previous webinars and application notes based from the Bruker website. For the purposes of this webinar, we are interested in the probe considerations for Q&M. Here, for the first time, we are not just concerned about the apex and that the apex of the probe is sharp. We're concerned with the overall probe shape and the radius, as they play a direct role in the calculations performed to turn a qualitative mechanical measurement into a quantitative mechanical measurement. So, to begin here, let's look at an example of a Q&M measurement, and then we'll return to discuss the probes. What we have here is a DMT modulus map of sample stiffness, shown with the corresponding cross-sections for topography and for modulus. Keep in mind that Nanoscope collects up to 8 channels of data simultaneously, so these images were acquired at the same time. The difference between the tie and sealant layers is not observed in the topography, which is the top plot, but is clearly seen in the modulus image. Probe considerations for this application are apex sharpness, as this is also a high-resolution image, but now when we think of the spring constant of the cantilever, we need to take into account the material properties of the sample. In order to perform a good Q&M measurement, the spring constant of the cantilever must match the stiffness of the sample. In this case, a TAP 150A is used, which also has a backside aluminum coating to reduce optical interference. Okay, so now back to the probes and a real quick discussion about 2 important models for Q&M, both the Hertzian and Sneddon. These are well-studied deformation models going back many, many years, and in the case of Hertz, all the way back to the 1880s. For the case of our case of AFM probes, we need to think about these models with respect to the probe shape, and more specifically, the probe shape as the probe deforms the sample surface. The apex of the probe can be thought of as spherical, and in that case of not deforming the sample surface significantly, the Hertz model is appropriate. Once the probe starts to deform the sample surface, we need to move over to the Sneddon model. In doing so, we need to understand the tip half angle correctly to apply the correct model. In either case, the cone half angle or the tip radius are simply entered into the Nanoscope software. So, for selecting a probe for an experiment, we want to select the largest tip that meets our measurement resolution needs. A large tip is going to be more stable and matches the models better, the trade-off here being lower resolution. A sharper probe will have a higher resolution, but deviates from the models more quickly and are more subject to change due to tip wear during the measurement. The spring constant of the cantilever must also be matched to the stiffness of the sample. The plot here the plot here is of the samples in the Q&M calibration kit, shown with the probes appropriate for measurements within those stiffness regimes. Though PeakForce tapping does not feed back on the cantilever amplitude, the resonant frequency of the cantilever amplitude is important in that we don't want the cantilever resonance to be close to that of the modulation frequency. A good rule of thumb here is that the cantilever resonance should be about 10x the modulation frequency. And lastly, shorter is usually better. A shorter cantilever has greater sensitivity and higher frequency with smaller viscous background effects. So, in this example here, we're looking at the performance of measuring modulus using an MLCTE probe on 3 different concentrations of agarose gel. As the percentage of agarose gel increases, the sample becomes stiffer, and the soft probe used is no longer stiff enough to perform a good measurement. The spring constant of the MLCTE probe, nominally 2 to 10 newtons per meter, matches the 1% agarose gel well at around 65 kilopascals, but matches poorly at the 5% concentration at around 1.1 megapascals. This can be seen in the good repeatability of the 1% measurement data set and the poor repeatability in the 5% data set. In our last Q&M example, we're looking at live cells on a glass-bottom Petri dish. On the right side of the image, we can see that the glass completely saturates the modulus signal. From the inset force curves, we can also see that for this experiment, the SNED model provides a much better fit than the DMT modulus. In this case here, as we shall see again shortly, a dull pyramidal tip is used so as not to damage the live cells. Here, an MLCTD probe with a very low spring constant of 0.03 newtons per meter and an end radius of around 20 nanometers with a half angle of 35 degrees is used. Okay, so now let's switch gears a bit and move from nanomechanical AFM into fast scanning AFM. Here we'll be looking at this in both air and in fluid. So, why fast scanning AFM? Well, quite simply, we don't live in a static world. Most of the interesting phenomena occur as systems change from one state to another. Fast scanning permits us to interrogate these systems and use the AFM to observe these dynamic processes. For static samples, fast scanning permits the rapid acquisition of large amounts of data to generate meaningful statistics of sample measurements. And lastly, fast scanning permits the acquisition of large data-dense images quickly. At speeds that traditional AFM speeds, collecting such images would be prohibitively slow. So, quick guideline for AFM selecting probes for fast scanning. We need to consider the resonant frequency and the quality factor. For tapping mode, the cantilever bandwidth is approximately the fundamental frequency divided by Q. Q depends on the fluid environment, air, water, etc., and the length of the probe. For PeakForce tapping, the resonant frequency and the modulation frequency should be high enough to have at least 1 tap per pixel. Shorter probes are always recommended, as shorter levers, as we've seen many times before, are higher frequency and are more sensitive. And the resolution is determined by the sharpness of the probe. Once again, the microscope maker's rule. So, in this example of high-speed AFM, we see 2 fronts coming towards each other, passing over defects, sometimes incorporating them and sometimes not. We can also see how, when the lamella pass larger defects, that some terminate while others go around. Ultimately, the 2 fronts join, and in some regions, the lamella join. In others, an interface is created. Okay, so now we're going to move from performing high-speed AFM images in air to capturing high-speed AFM images in fluid. When choosing a probe for high-speed imaging in fluid, we want to select a probe that has a short or ultra-short soft cantilever with a low spring constant and a high resonant frequency. This combination of mechanical properties produces probes with a high bandwidth that are soft enough so as not to damage the soft samples or samples that are weakly bound to supporting substrates, and to be able to do so at high scan speeds. It is important to note here that the resonant frequencies quoted by manufacturers is the resonant frequency in air and not in fluid. In general, the resonant frequency of a cantilever is reduced by 1/2 to 2/3 in fluid as compared to its resonant frequency in air. As with air imaging, the sharpness of the probe will define the imaging resolution capabilities of a probe. For high-resolution images of a sharp probe is required. Using a probe with a short cantilever and therefore greater force sensitivity permits the use of a sharp probe on these delicate soft samples. In the example shown here, we can see the individual strands of DNA in the DNA origami when scanned at up to 43 Hertz. A Fast Scan DX probe was used to capture these images. Next, we have an example of high-speed imaging in fluid of lambda digest DNA. Parts of the DNA are loosely bound to the surface and move from frame to frame. Examples from 1/2 frame per second to 3 frames per second are shown. Again, we're using a short, soft cantilever with a high resonant frequency and a very sharp probe. The probe sharpness is required to resolve the molecular structure, and the high resonant frequency permits the fast image acquisition, and the short cantilever provides the force sensitivity required to preserve the sample. As this image is acquired in tapping mode, we also need to have a probe that is stiff enough to be able to oscillate in fluid, but is not so stiff as to damage the sample. In this case here, the probe used was the Fast Scan DX probe. Here's another example of high-speed imaging in fluid. In this case, we're observing the cell membrane dynamics of live E. coli cells. In order to resolve the 2D organized porin molecules, a sharp probe is required, and in order for this probe not to damage this delicate sample, a small cantilever is used to reduce the imaging forces. So again here, we're using a short, soft cantilever with a high resonant frequency and a very sharp probe. The probe sharpness is required to resolve the molecular structure. The high resonant frequency permits the fast image acquisition, and the short cantilever provides the force sensitivity required to preserve the sample. As this image is acquired in tapping mode, we again need to have a probe that is stiff enough to be able to oscillate in fluid, but is not so stiff as to damage the sample. Again here, the probe that we've decided to use is the Fast Scan DX probe. So these last two examples of high-speed AFM in fluid are a good segue into our next topic, which will be biological applications of the AFM. So in choosing probes for live cells in fluid, we want soft cantilevers with a low spring constant. For live cells, we also now need to think about the coatings. If any is to be used, as the typical aluminum coating can contaminate biological samples. Lastly, for tip sharpness, we now need to be concerned with probes being too sharp. Sharp probes are excellent for high resolution to single molecule imaging, but may damage live cells. For live cell imaging, a blunted probe may be more preferable. Here we're looking at molecular imaging of biological samples, in this case aquaporin and bacteriorhodopsin, and in that we are interested in the molecular structure. We want to use a sharp probe with a small end radius. Also here for the first time we are coming across contact mode with fluid. For imaging in contact mode in fluid, we also want to use a very soft, very low K cantilever. The recommended probes for this experiment are the MSNLC or the SNLD probes. PeakForce tapping for molecular imaging in DNA is used for imaging DNA in fluid. Here again, we need a very sharp tip for the resolution of the molecule, but now we are using a cantilever soft enough and to have an intermediate spring constant. The cantilever must still be stiff enough to be able to oscillate in fluid. The recommended probes here are the ScanAssist fluid or the SNL-A probes. In our next example, we're looking at contact mode imaging of live cells in fluid. Here we want a very soft, low-kick cantilever, but instead of the sharp tip used for imaging the aquaporin and bacterial rhodopsin in contact mode in fluid, we now want a blunted probe. Imaging live cells does not require the high resolution that the molecular imaging did. Here it is more important not to damage the live cells. The lower pressure afforded by the larger tip radius is ideal. The recommended probes for this application would be the MLCTC, the DNPA, or the OBL probes. And in our last example here, we are performing a Q&M measurement in PeakForce tapping on live cells. As we are interested in the molecular structure, we're going to use a sharp probe with a small end radius. As this is PeakForce tapping, we also need to use a probe with intermediate K so that the cantilever is stiff enough to oscillate in fluid. Recommended probes for this application are the DNPA probes, the MLCTF, and the ScanAssist fluid probes. So next we're going to investigate probes used for force spectroscopy, and for the most part we're going to be discussing force spectroscopy in the context of biological applications. AFM force spectroscopy is the localized measurement of modulus in molecular unfolding and binding interactions. When performing these measurements, we have many of the same considerations that we did for Q&M. We want to choose the cantilever spring constant based on the expected stiffness of the sample for modulus and indentation measurements, and on the expected binding energy for the unfolding and unbinding measurements. The measured cantilever deflection should be within 2 to 3 volts of the non-contact deflection value. If the probe is too stiff, there will be no deflection to measure. If the probe is too soft, the deflection is so large that the photodetector response becomes nonlinear. Lastly, it is important to calculate the deflection sensitivity and the spring constant, as these nominal values are not accurate. So using coated probes is important in force spectroscopy to mitigate the optical interference. However, aluminum-coated probes are not ideal for biological applications due to contamination. In these cases, a gold coating is preferred. Using an uncoated probe is not ideal, but may be necessary in cases where the coating induces drift. If you are using a non-coated probe, it is important to be aware of the risks of optical interference within your experiment. Like the considerations for Q&M, understanding the tip shape is very important for modulus measurements and for the selection of the appropriate model to be used, either Hertz-DMT or the Snedden. As for the tip sharpness, a blunt tip will minimize the pressure exerted and thus can reduce the tip or sample damage. For unfolding or unbinding experiments, a large probe radius will increase the likelihood that a molecule will attach to the end of the probe. In this example of optimally targeted cell modulus measurements, force curves were performed on live endothelial cells. These cells were fluorescently labeled with a membrane potential indicating dye, bisoxanol. Cells were found to be stiffer in their hyperpolarized state than they were in their depolarized states. The probe that was selected to perform this measurement were blunt so as not to damage the cell membranes, with a very soft cantilever to match the low modulus of the cells. The recommended probes for this application are the MLCTC, or spherical probes. Here we are looking at an AFM pulling and unfolding curve for a single Titan 8-mer construct. The retract portion of the curve shows the classic sawtooth pattern with an approximately 200 piconewton force required to unfold each of the 8 repeated subunits. The cantilever used here has a very low spring constant to match the piconewton range of the binding forces. A large radius probe was used to increase the likelihood of the Titan 8 molecules binding to the probe. The recommended probes for this application are the MLCTC, the MLCTD, and the DNPD probes. So, with that said, let's move on to discussing some of the other applications and the probes chosen for those applications. And what we're going to be looking at here for the electron modes will be focused on the Kelvin force probe microscopy, KPFM. KPFM is a combination of the Kelvin probe technique used to measure surface potential with AFM to enable the measurement of surface potential at the nanoscale. The two methods for KPFM modes, AM and FM, may be combined with the two major AFM modes, tapping and PeakForce tapping. For each mode combination, the probe recommendations can be found in the nanoscope experiment selector as well as in the table above. Although the KPFM's lateral resolution is largely determined by the KPFM mode used, for example, FM KPFM is far better than AM KPFM, the probe geometry also plays a role. The electric force is a long-range force, and thus it not only interacts with the probe apex, but also the entire cone of the probe and the cantilever as well. To mitigate these secondary interactions, it is recommended that a probe with a higher aspect ratio and smaller cantilever be selected. The sensitivity of KPFM is proportional to the Q of the lever at the sample surface and inversely proportional to the spring constant of the lever. Thus, when choosing a probe for KPFM, a probe with a higher Q with a soft lever will increase the sensitivity of KPFM. As a point of reference, the Q is calculated by nanoscope as part of thermal tune, and I've highlighted this here on where to look on the thermal tune window to determine the Q of the cantilever that you're using. It is apparent that smaller spring constant and a larger Q of the cantilever will benefit the detection sensitivity of KPFM. After all, the lever is a force gradient sensor. Smaller K is gives a bigger response to a force or a force gradient change, and Q amplifies the response, and therefore a bigger Q is better. In this table here, we've summarized a comparison of the Q and K values for probes commonly used for KPFM. And what we can see here is that the PFQ-NE-AL probe and the SCM-PIT have similar ratios of Q to K, and therefore similar KPFM sensitivity. In this case, then, the deciding factor comes down to the fact that the PFQ-NE-AL probe has a sharper apex and therefore a higher spatial resolution. And that it is made from a single material, it is better for measurement repeatability. This is why the PFQ-NE-AL probe is the #1 choice across the board in the previous table for the best probe choice for KPFM in ambient conditions. As a point of reference, in all cases, the same probe under ultra-high vacuum would have approximately 100 times a higher Q and then much better sensitivity. So with that said, let's move on to discussing some of the applications and probes for the nano-optical microscopy. And in specific for nano-optical, we're going to focus on TERS, or tip-enhanced Raman spectroscopy. Tip-enhanced Raman spectroscopy uses a probe to enhance the Raman output signal when the probe is brought into close proximity to the sample under investigation. The common two types of feedback here are STM and AFM. The enhancement provided by STM tends to be better because the STM probe is able to be brought within closer proximity to the sample surface than the AFM probe. The probes used for TERS are made out of gold or silver for the best plasmon enhancement, which requires low losses and high carrier density. Gold is preferable to silver, as the silver is less durable and less consistent due to tarnishing. Here we have a bit more of a detailed comparison of the use of STM probe to an AFM probe. The STM probe can be brought into closer proximity to the sample surface and therefore will have a greater enhancement. However, the STM probe does require that the sample be conductive. The new AFM probe, though not providing the level of enhancement of the STM probe, benefits from being able to work on any substrate rather than being restricted to conductive substrates. Examples of the tuning fork and STM probes are shown here at the right. Here are several examples of the enhancement provided by the probe. In these cases, we see that the TERS signal output in red is greatly enhanced over the far field performance in blue. Again, here, the mechanisms behind why this enhancement occurs is beyond the scope of this particular webinar, but I do encourage you to watch the recording of the Advanced TERS Applications webinar available from the Bruker website. Lastly, I would like to mention that as the only company that produces both STM and tuning fork probes for TERS, Bruker has invested heavily in assuring that our out-of-box quality and probe consistency and performance meets our customers' needs. Testing of these probes has shown a greater than 80% 10x enhancement performance. So next I'd like to move on to probe preparation and cleaning. So here we're going to present some tips for cleaning tips. What we've got is, first we want to mention that probe cleaning is not a recipe for cost savings. The main purpose for doing any sort of probe cleaning is to prepare the probe for an experiment. Only in rare examples such as the DNSP probe are these probes actually what we consider to be recyclable. Some examples of pre-experiment probe preparations would be ethanol and isopropanol, UV light plus some DI water for removing organic materials, plasma etching for functionalizing and oxidizing tips, acidic piranha for functionalizing probes, and ultrasonication. Again, with the ultrasonication, it's going to be very difficult to hold the probe. So again, for a bias review of recovering your tips, basically, as we think about recycling our tips, we want to put some thought into this. So first, from a cost-benefit analysis, can you change the probe without disrupting your experiment? If at all possible, change your probes. As a last-ditch effort, if probe change is not practical, some methods that have occasionally been shown to work would be to retract the probe, running the AC drive at a very high run frequency, sweep several times, and this occasionally works in fluid. You can approach the sample while in contact, increase the feedback to cause the tip to oscillate. We can perform what is called a controlled crash using a low set point. We can scan a clean glass slide in contact mode, or pressing into a soft sample such as BOPP. The special cases such as nano indent probes, which are very expensive, durable, and are therefore recoverable by making a forced indentation into gold or rubber, or STM probes, it is possible to make the nanospherity with a hard contact, though this has a low success rate. So lastly here, I'd like to take a quick look at the Bruker AFM Probe's website. So in wrapping up this morning's webinar, I'd like to briefly turn our attention to the Bruker AFM website. We have covered a large range of applications this morning, and the selection of an actual probe may still seem daunting. To help our customers quickly and effectively choose the best probe for their experiment, the Bruker AFM Probe's website offers a number of tools to help with the selection process. First, we have the Probe Selection Wizard, which allows you to enter the type of AFM that you have, the application or experiment that you would like to perform, the mode which you would like to use, and the sample you wish to investigate. Some or all of these fields may be entered to narrow your search and help you select the best probe suited for your needs. Along with the wizard, you may simply search through the selection of probes from the general menu, which will bring you to the advanced selection guide, from which you can choose probe by mode, by application, by AFM, or by sample. And through this portal, you'll also be directed to the advanced product filter, from which you also may define the types of experiments that you wish to perform to receive a well-tailored selection of probes to suit your needs. So in conclusion, again, to reiterate that the appropriate selection of an AFM probe can be one of the most important decisions that you make towards a successful AFM experiment. Although there are many probes to choose from, and this selection may appear daunting, the application's requirements usually point to a clear path for probe selection. The Bruker website has distilled this information for the user to help make the probe selection as an AFM expert does. And the Bruker applications and probe teams are always available to assist our customers in making the best probe selection for their needs. I'd like to thank you very much for your time this morning.
All right, great. Thank you very much, Sean. It was a great presentation. We have a large amount of questions coming in. I don't think that we're going to be able to get to the answers, all of them, in the live session here. But as I mentioned earlier, we will absolutely follow up with all these questions to get you the information that you need. It seems that the questions, there's a couple sort of major categories which I'll try to get together. I'd say primarily they're dominated by specific applications, questions about what probe to use in what situation, and so we'll definitely follow up with you there, though I'm not sure I'm going to be able to answer all those. So let's just try to go through some of these. I'll start with some of the questions that came in earlier, more on the AFM or general questions, and then actually fairly quickly moved into the specific applications. Okay, so in general, at the start you said that tips with higher resonant frequencies are better. We had some interest in why you said that.
We did not get into this in detail in this presentation because we were trying to take it from the probe's perspective. In short, a higher frequency probes are typically lower noise because the thermal noise is spread over the entire bandwidth to the first resonance, and they're typically faster.
Okay. This question came in but before you did the cleaning, but I think it's probably still relevant. In order to preserve AFM probes, to what degree of vacuum, I guess that would be, or desiccation is required? Is 100 millibar enough?
So in general, we don't find that the storage in vacuum is required. We've been able to image high resolution right out of the box. Let's say please follow up with what specific problems you're having with your imaging or contamination.
Okay. Also on cleaning, I have some colloidal probes, bead borosilicate, that are dirty. How do I clean them?
I think that was asked, excuse me, I think that was asked this before the cleaning slide. Following these steps can be, one should be cautious of the adhesive used to attach the bead to the cantilever. Make sure that any solvents you use don't dissolve it.
Yeah, that might be a category, yeah, where you would want to try to recycle, but I guess yeah, be cautious. Okay, I think now we're going to transition over a little bit to the some of the applications, but this is still a little bit of a tie together. Is there any sample available for cell stiffness determination?
So we currently do not have a commercial solution for this, but I know the team is experimenting with standards and probes for this. I will pass your question on to one of them. There's also a fair bit of research on this and in the community to standardize this. I believe the cost of the action in Europe has been a big effort on this.
I guess this is just a quick question. Yeah. At the Q&M section, the cell on glass with the saturated modulus signal, was that a live cell or a fixed cell?
It was a live cell.
Okay. Sort of along the same lines of, or this is still in QM, how do you match the sample stiffness, I guess the question is, to the probe stiffness if you're trying to figure out what the sample stiffness is?
That's a very good question, and you do have to iterate to find the right match. It is pretty clear when you're scanning whether you cannot get enough deformation or you cannot get enough signal, and that lets you know pretty quickly.
Okay. Okay. Let's see here. So now moving more into the these are sort of into more just the specific questions of what probe is right for the job here. So I've just started using MLCT probes with PeakForce Q&M, and I'm having trouble getting a nice stable heartbeat. What's the best approach for using soft cantilevers with PeakForce tapping? And they have a dimension icon.
Just as I guess I would need to know a bit more to really troubleshoot it properly. But provided the adhesion is not too much, use a larger modulation amplitude and I guess maybe a lower modulation frequency. Start with a stiffer probe to get a feel for the app, and then slowly move down in spring constant to understand the limitations of your system.
Okay. Which probe would you suggest to study protein aggregation and aggregation structures on mica using PeakForce tapping or ScanAssist on an icon?
So for PeakForce tapping, I would suggest using the ScanAssist Fluid Plus probe. If it's too stiff, then I'd switch over to the SNLD probe.
Okay. What is the recommended probe for Q&M of biomaterials with a modulus range of 2 to 5 gigapascals? I guess the question is either an air or liquid. This is sort of as a follow-on. What's a recommended substrate for mounting? And you need to calibrate the tip radius each time for different samples, even if you're using the same probe type and if you're using the absolute calibration method.
So to answer the first part, would be a TAP 525 or an R-TESPA probe. Use the graph for a real quick reference, as it should be in this graph should be in the manual. For the substrate, silicon mounted on a magnetic puck is a good place to start. And yes, if you want accurate results, you really do need to perform an accurate calibration.
Yeah, I think that's it's a good point about the last one. The level to which you can get quantitative results out of Q&M really has to do with the level that you calibrate. That said, we do have a lot of people who sort of work just in the qualitative mode to get contrast, and then okay. So we actually had several questions in the live cell part about the different options in terms of different radius, and when you're talking about the blunt tips. So what radius of blunt tips are available?
So generally, for Rayler probes, we have sharp and blunt. Where the blunt is in the 20 nanometer end radius range. To get a larger radius, you need to switch to a really spherical probe. For these, we sell tipless cantilevers, so you can actually build a probe that best suits your needs.
Okay. While using MLCT tips, and these are the tips that have multiple cantilevers coming off the edge of the die, I guess the question is, do you cut off the extra tips or leave them off the chip, or leave them on the chip? And if you're doing cell imaging, or I guess the question is, if you in fact cut them off, how do you cut them off?
So if you're using one of the shorter cantilevers, you must cut the other cantilevers off. If you have a sample where you think that the shorter cantilever will hit, it too must come off. To do this, generally just brush it with a pair of tweezers. They tend to come right off. I've also used vacuum, a little vacuum tweezer.
Okay.
It sucks it right off. Yeah.
Okay. Let's see. So we're a little short on time, so let's make this the last question. Could you please recommend Could you please recommend a Bruker probe for imaging live tissue and fluid?
So this would be the same as the ones we recommend for cells. However, is your tissue is microtome thin? You can use a sharper probe. If it is thick, if it's thick, then you can use the same as the live cells.
Okay. Very good. So I'd like to thank all of you for attending this webinar, as well as thank Sean for the presentation. We do have some additional slides to, some additional questions which we will answer personally in a follow-up email. Also, I know there's a lot of information in this webinar. I'd say probably one of the most common questions was, how do you get the download? And it'll be available on the website along with the other webinars shortly after the presentation concludes. And then finally, as you sign off, you'll be asked to take a survey, and again, we'd really appreciate it if you could fill that out. Okay, and with that, I will conclude today's webinar. Thanks again for attending. Bye-bye.